Bennett said we are learning more about statistics today. I'm pretty excited because this unit has been a lot of fun.
Today we will be playing a game called Even versus Odd in Partners. You will look at the outcome of your games and try to determine if the game is fair. You will each take turns rolling the pair of dice, and if the sum is even, the even player wins. If the sum is odd, the odd player wins. Keep a record of who won each of the 10 rounds. After you are finished your 10 rounds, enter the data from your group into the Socrative quiz and also answer question 2.
Okay, I will be even and you will be odd. I'll roll this first time. Oh look, I rolled a 7. Looks like you win this round. Your turn to roll.
Okay, now it's my turn to roll. I rolled a 5, which means I win. Maybe this game isn't fair. Let's see how the next few rounds go.
Okay, so after 10 rounds you won 7 times and I won 3 times. This game must not be fair.
From the information entered into Socrative, these are the results from our class experiment. Do you think this game is fair? What if you could see results for more rounds? Work with your partner to define fairness and calculate the probability for this game. Then use Tinker plots to figure out how many rounds you would need to show this game is fair.
Fairness is when everyone has the same chance of winning. Looking at this game, it doesn't seem to be fair.
Okay, now let's look at our probability for each number. There is more than one way to make some of these numbers.
Look. 7 happens more than any other number. So maybe it isn't fair.
But if we count up how many possibilities there are for even and odd, they are the same. So it is fair.
This is the probability chart for the sum of a pair of dice. It looks like 7 has the highest probability of happening. Let's add up the percents and make sure they are even.
It is easy to add up the fractions since there are a lot of repeating decimals. They both are 1836, which is exactly half. So the theoretical data says this game should be fair.
Now let's look at more rounds and see if we can get more fair results than our class data. Let's start with 100 rounds. Oh, that doesn't look fair at all. Maybe we need to do 500 rounds.
This looks really fair. I wonder if it would ever come out exactly even.
Let's start with 50 rounds. Wow, that is more uneven than our class data. Maybe this isn't fair. We should try more rounds.
Let's try 100 rounds. That looks pretty even. I think we can say with 100 rounds this game is fair.
I think 1,000 rounds will be the best way to show if it is fair. Oh goodness, it doesn't seem to be fair. 1,000 rounds is a lot. Why didn't it work?
Well, I guess we need a lot more rounds. Let's try 5,000. Oh, this seems to work out well. 5,000 rounds shows that the game is fair. I would not want to do that many rounds by hand.
Maybe we should run another set of rounds just to make sure it still looks pretty even. Oh, wow, this one came out really close to exactly even.
Let's talk about what amount of rounds you and your partner decided were needed to show that the game was fair. I would like a representative from each group to share.
We decided that 500 rounds seemed to show the game was fair. We also noticed that the simpler distribution matched our distribution of sums.
That is a great observation, Ivy. Your distribution of sums is shown in the bottom middle on Tinker plots. Your distribution here should match your probability distribution.
My group tried 50 rounds first, but it was pretty uneven, so then we tried 100 and it looked almost exactly even, so we decided that was enough to show the game was fair.
Joey, did your group notice that we actually did very close to 100 rounds as a whole class? We already knew 100 might not be enough, but your totals came out a lot closer to fair. Did any group run more than one test after you decided on a number of rounds? One sample could be very different from another.
Actually, we did. At first, we thought 1,000 rounds would be enough, but our first outcome was pretty uneven. We then picked 5,000 rounds and it came out pretty close to even. So then we decided to try 5,000 rounds again to make sure. We got 2,503 and 2,497, which is so close to being exactly 50% each. This really matched up with the predicted probability.
I have heard some great discussions as I have walked around. I really think that each group did a good job adjusting their number of rounds after the first guess wasn't perfect. For homework tonight, think about how the experimental data you and your peers saw in class today compares to the theoretical data you calculated. Write down your thoughts.